Welcome to part 2 of our never-ending lecture on electronic structure and bonding. I'm Dr. Mike Christiansen, and today I'm going to teach you about electronic structure and bonding. As I ponder this subject, it reminds me of time when I sang for a high school performing choir as a high tenor. While singing an epic song with our large choir one day, I eagerly awaited an upcoming part when we tenors got the chance to belt out a really long and sustained note. It just so happened, however, that at that time I also really had to belch. So what could I do? Well, in my adolescent immaturity, I reasoned that I should just do both things at the same time. Thus, when the time arrived for us tenors to belt out that note, I instead released a loud and vibrant belch, which I stopped perfectly when the conductor cut us off at the end of the sustained note. Bob Christiansen, my conductor, was furious. "Who did that?" he said, looking around in the tenor section. "It was me," I proudly exclaimed. "Mike!" Mr. Christiansen exclaimed. "Bob!" I replied. "Get out of here!" he yelled. I was expelled for the rest of the day. And as you might have surmised from the story, I was a defiant little turd in high school. That notwithstanding, I still managed to become a successful chemistry professor. So yes, there is hope for all of us, even for those of us who suck. Before vaulting into today's material, then, let's take a look at the things that you should be able to do after this lecture is done. 1. Sort bonds by strength and length. And 2. Identify any atom's hybridization and explain in terms of atomic and molecular orbitals what that actually means. So here's that information, or if I were saying it in Spanish, aquí está la información. In the wondrous mental colonoscopy that is the world of covalent bonding and orbital overlap, you must know the following. In any molecule, each single bond in the molecule is called a sigma bond. All double bonds contain one sigma and one pi bond, and triple bonds all contain one sigma and two pi bonds. This is illustrated by the following example, supplied by my amazing staff that consists both of myself and a plush Darth Vader desk toy sitting in my office. This molecule, CH4, is also known as methane, which, incidentally, is the most politically disconcerting ingredient found in cow flatulence. As you can see, this molecule methane has 4 carbon-hydrogen single bonds, which means that it has 4 sigma bonds. This molecule, formaldehyde, was once used as an embalming agent. As you should be able to surmise, the carbon-oxygen double bond, because it is a double bond, contains one sigma and one pi bond, while each CH single bond is a single bond and therefore is a sigma bond. Here's another example. This molecule is known commonly as acetylene, the very compound used in acetylene welding torches and in Keith Richards' hangover medication. That was a joke. Anyway, I once detonated a balloon containing acetylene gas just for fun. It turned into a large black fireball, but that's neither here nor there. The point is, the carbon-carbon triple bond in this molecule, as well as all triple bonds, contain one sigma bond and 2 pi bonds. Each carbon-hydrogen bond in the molecule is a single bond and is therefore a sigma bond. The final point I wish to make here is this. Sigma bonds are stronger than pi bonds. However, a triple bond is overall stronger than a double bond because it has 1 sigma and 2 pi bonds. By the same logic, a double bond is a little stronger than a single bond because it contains 1 sigma and a pi bond. Typically, the stronger the bond, the shorter it is in length. Hence, single bonds are longer than double bonds, which are longer than triple bonds. So that brings us to a lecture question. Which of the following has the shortest carbon-carbon bond length? A, B, C, or none of the above? I'll now readdress this ever-forgettable topic of atomic hybridization. Now, there are 2 different ways of learning hybridization, the easy way and the hard way. I, of course, prefer the easy way for everything. But on this topic, to be quite honest, you really have to learn both in order to understand what's going on. So I'm going to teach them both to you. First, we'll talk about the easy way. If I'm ever asked to determine an atom's hybridization, all I do is count how many things are around that atom. You can see me giving you this table right here. Now, the number of things around an atom, I should say, refers to how many other atoms or lone pairs are around them. So when I say a thing, I'm talking about another atom or a lone pair. So we count how many things there are, and then we memorize this chart. 2 things is an sp hybridized center, 3 things sp2, and 4 is sp3. And that should get us deep enough to be able to answer any of the types of questions that you'd encounter on a standardized exam in this subject. Let's see if we can look at some examples. What is the hybridization of each of the indicated atoms? Let's start at this one. See this carbon? We're going to count how many things are around it. By things, I mean atoms or lone pairs. This carbon has a hydrogen, a hydrogen, a hydrogen, a hydrogen. I'll hold up that. I count to 4. There's 4 hydrogens. So what's its hybridization? It's sp3. 1, 2, 3. sp3. Let's look at the hybridization of this carbon atom. How many things are around it? I've got a hydrogen, and an oxygen. Now this is one of those things that some students get confused about. They think that because there's a double bond here, I'm going to count that somehow as more than one thing. You do not. All we do is count how many things are around it. A hydrogen, and an oxygen. The hybridization of that is sp2. Let's see if we can figure out the hybridization of this oxygen. How many things are around it? It's got a carbon down here, lone pairs over here, and lone pairs over there. sp2. See that? What's the hybridization of this carbon atom? Once again, we count how many things are around it. We don't care that there's a triple bond or a double bond or a quadruple bond or a sextuple bond. That is irrelevant. We just look and count how many things are around it. 1 hydrogen to the left and a carbon to the right. There's only 2, so it is sp. Does that make sense? This is the easy way to determine an atom's hybridization. Now, as I indicated before, I am going to teach you the hard way. But before I get to that, I want to also re-solidify in your minds what we've taught before about atomic bond angles. I want you to tell me what are the indicated bond angles. In this molecule that we decided has an sp3 hybridized carbon in the center, what is the bond angle between all of these hydrogens in this tetrahedral structure? You should have remembered it is 109.5. What about right here? This carbon only has 3 things around it in a trigonal plane structure. What's the bond angle? It's 120. And the bond angle right here, this carbon is in a nice straight line. It's 180. Thus we can see that an sp3 hybridized carbon will try to get its 4 groups to be around 109.5. An sp2 hybridized carbon will try to get its groups to be 120. And an sp hybridized carbon will try to get its groups to be around 180. It's not always dead on those numbers, but it tries as best as it can to match them. Now to the hard way, which is my way of saying now I'm going to actually teach you what's really going on. I'll of course be talking about orbitals, which is a subject that often makes people poop their pants with fear. Please don't do that, because I don't think anyone would appreciate cleaning up the mess. To simplify things, I want you guys to imagine that orbitals are really nothing more than a region of space that electrons can occupy. Orbitals are in essence just empty parking places for electrons to go into. Different orbitals, of course, have different shapes. S orbitals are shaped like spheres, and p orbitals are shaped like cute little dumbbells. Now, as you should have learned back in general chemistry, every element has its own electron configuration, which is a subject that I won't review here. Carbon's electron configuration, of course, is 1s2, 2s2, 2p2. Now, carbon's valence orbitals are the ones that have the highest number, this 2s orbital and this 2p orbital. You count up the number of electrons occupying those, it adds up to 1, 2, 3, 4. So that means that carbon has 4 total valence electrons. Now let's see if we can assemble a carbon atom one layer at a time. We'll imagine that carbon's nucleus looks like this. This is where its neutrons and protons are located. This nucleus is surrounded by a 1s orbital. Now if you look up here, you see how it says there are 2 electrons that occupy that 1s orbital? There they are. These are core electrons. Now outside this layer we see a slightly larger 2s orbital. Over here in the electron configuration it says there are 2 electrons that occupy that 2s orbital. There they are. Now these are 2 of carbon's valence electrons. Outside of this layer, we see carbon's 3 individual 2p orbitals, which straddle the x, y, and z axes 90 degrees apart from each other. Now each of carbon's if we look over here, you'll see that the electron configuration indicates that there are 2 electrons in carbon's 2p orbitals. Where do those go? They go right here and right here. The third 2p dumbbell right here remains unoccupied. So let's pretend that carbon wants to bond with 4 separate hydrogen atoms to form methane, the molecule shown here. Now once again you'll remember that the bond angle in this tetrahedral structure is 109.5 degrees. So here come our 4 individual hydrogen atoms ready to bond with carbon. In order to form a bond, each of these hydrogen atoms, which has an individual 1s orbital filled with a single electron, has to overlap with carbon's valence orbitals somehow, so that their joint electrons can be shared in those molecular orbitals. Now look at this. How in the world are these hydrogen atoms going to be able to overlap with carbon's 2p and 2s orbitals? Where could they go? Well, we could imagine this hydrogen atom right here might be able to overlap with the bottom of this p orbital. Okay. And this hydrogen atom over here could potentially overlap with this p orbital, and this hydrogen atom could overlap with this p orbital. But if it did that, now all 3 of these hydrogen atoms have overlapped with 3 of these p orbitals. What's left for this poor hydrogen atom over here? Where can he go? Well, the only thing he could overlap with is the 2s orbital, which is kind of a little bit located, squished in here in the interior. So he'd have to kind of squish down in there. And that might create some real problems for him to be able to fit into that hole. There's another problem here too. Each of these p orbitals are located 90 degrees apart, not 109.5. So even if these 3 hydrogen atoms did latch on and overlap with these p orbitals, they're not going to be 109.5 apart. They're going to be 90 degrees apart, and then this hydrogen atom is going to have to somehow squish down so that it can fit into this 2s orbital here. This whole situation stinks, much like methane gas itself. So what in the world can carbon do? What carbon does is it takes its 3 2p orbitals, shown here, and its 1 2s orbital, and it combines them. So if you could imagine that these 4 different orbitals, the 3 2p orbitals and this 1 2s orbital, if these were all made out of molding clay, and I took them in my hands and squished them all together, and then I took all of that molding clay and separated it out equally into 4 separate orbitals that are all equal size and shape. That's essentially what carbon's doing. It's taking these 3 individual 2p orbitals, this 1 2s orbital, squishing them together, and separating them out into 4 separate and equal sp3 orbitals. Carbon now places each of these new sp3 orbitals together in this kind of 3-dimensional form. And guess what the bond angle is between them? 109.5. Carbon can put its 4 valence electrons in each in one of these 4 sp3 orbitals. Now what can happen? Well, now each of these 4 hydrogen atoms can come right in there, 109.5 degrees apart, overlap with these 4 sp3 orbitals, and form a nice, beautiful molecule of methane. Isn't that pretty? That's what orbital hybridization is. The word hybrid comes from a Latin root that essentially means mixing or combining. So what it's doing is it's taking an s orbital and some number of p orbitals and squishing them together to make new orbitals. Does that make sense? Well, let's see if we can figure out and apply it to a different kind of hybridization. As you might remember, the hybridization of this carbon is sp2, and the bond angle should be about 120 degrees. So what does that mean? Well, it means that carbon has combined its 2s orbital and only 2 of its 2p orbitals together in this hybridization. Let's see if we can take a look at that. So carbon's taken 2 of its 2p orbitals and its 2s orbital, squished them together, woo! And then made 3 individual equal sp2 orbitals like that. These 3 individual sp2 orbitals are then laid down in a trigonal planar structure like this. This is supposed to be all on a plane with a beautiful 120 degree angle separating each of these lobes. Now you'll notice when we contrast this pattern with what we saw in the previous slide that carbon in this case left 1 of its 2p orbitals out. It only used up 2 of these in this hybridization process. So what happened to the third 2p orbital? Where is it? It's right here. It goes above and below the plane of these 3 individual sp2 orbitals, 90 degrees perpendicular to that plane. That's what an sp2 hybridized carbon center looks like. Our carbon atom is now hybridized and ready to go. It places its 4 valence electrons, 3 individually, into its 3 sp2 orbitals, and 1 into its perpendicular 2p orbital, which was left unused in the hybridization. Now oxygen, which is also sp2 hybridized in this molecule, comes in. Oxygen has 6 valence electrons, which occupies orbitals like this. These 2 electrons, which are coupled here in one of these sp2 hybridized orbitals, as well as these, represent these lone pairs dangling off of the oxygen like so. Now oxygen comes in, and these 2 atoms overlap to form this. This bond between oxygen and carbon here in the center is a sigma bond. This perpendicular overlapping bond between the unused 2p orbitals in both atoms is called a pi bond. Now I don't want you to be confused here. A pi bond kind of looks like 2 bonds. There's a line on top and a line on bottom. Don't think of that as 2 bonds. That is 1 pi bond. It is a pi bond, or a bond formed by unused 2p orbitals overlapping. It is not as strong as a sigma bond. Now at this juncture, the hydrogens can come in, overlap with these orbitals in the carbon atom, and form this molecule that we have right here. Now let's do the same process for an sp hybridized molecule, which has a 180 degree bond angle right here. The fact that these carbon atoms are sp hybridized implies that they've used up 1 of their s orbital and 1 of their p's. And they've left the other 2 p's unused in the hybridization. So let's take a look at that. We've taken 1 of our 2p orbitals, 1 of our 2s orbitals, and we only have 1, combine them to form 2 sp orbitals. When these sp orbitals are thrown together on the carbon atom, they form a nice 180 degree angle linearly like this. So what in the world happens here? Well, the unused 2p orbitals go perpendicular to the plane, 90 degrees apart from each other. So once again, let's go back. This carbon atom used 1 of its 2p orbitals. The other 2 2p orbitals remain unused, being perpendicular to each other and to the plane, which is occupied by these 2 individual sp orbitals. So what occurs next? Well, here are my 2 carbon atoms, both sp hybridized, with their remaining unused 2p orbitals lying perpendicular to each other, as shown here. At this point, they fill their orbitals with their respective valence electrons. They then overlap like so. Now this bond between the carbon and the other carbon is a sigma bond. These perpendicular overlapping bonds are each separate pi bonds. Once again, this circuit here is one pi bond, and this circuit here is a second pi bond. That represents the triple bond. These hydrogen atoms can now come in, overlap with these lobes dangling off of the end, ultimately making this molecule. Which brings us to another lecture question. Choose the correct hybridization for the leftmost carbon atom in the following molecule. Is it sp, sp2, sp3, or none of the above? And here is another. Which carbon or carbons in the following molecule is or are sp hybridized? Now this slide features a series of questions that I've added just because I think they're fun. These are the types of questions that I personally have seen shown on standardized exams, such as the GRE, the MCAT, and the DAT. I thought that I'd just give them to you, just for the sake of enjoyment. Question number 1. How many sigma and pi bonds are there in the following molecule? Question 2. In a carbon-carbon double bond, A, hybridization occurs between the s orbital and one p orbital. B, hybridization occurs between the s orbital and two p orbitals. C, hybridization occurs between the s orbital and three p orbitals. Or D, hybridization occurs between the s and one p orbital. Question 3. Pi bonds are formed by which of the following orbitals? Two p's, two s's, one s, and one p, or all of the above? Question 4. How would one best describe the orbitals required to form a pi bond? Parallel overlap of two s orbitals, overlap of an s and a p, perpendicular overlap of two p's, or parallel overlap of two p's? And question 5. What is the hybridization of beryllium in the molecule BeH2? So that brings us to the end of today's lecture. I hope that it's been as enjoyable for you as it has been for me. I hope you'll stay tuned for our next lecture, which will finish Chapter 1's discussion, focusing on acids and bases. Until then, have an enjoyable rest of your day.